inside the recording. And then after the recording, I start sharing, which sometimes I didn't. So they saw my face and my voice, but I couldn't see the slide. So it happens. So just be careful. Some people don't do recording at all, so no complaint. I will remove this stuff from Zoom. Anyway, there is a way to remove it. It was stay whatever you want. There is plenty of room. What did you see her? She's Sumati. She's the new organic. She will take over my part after we finish the spectroscopy in a couple of weeks.
I think I start next Friday.
Okay.
Yeah.
And
Next week Friday. Yeah.
so we'll do a lot of asymmetric synthesis. Again, I told you already, probably lots of stuff connected to retrosynthesis. So please stay with us with retrosynthesis because it's going to be very useful. So for instance, today,
For 5 minutes and then
as long as you want. Mark. So you know that, for instance, I hope you watch the videos as usual, and as usual, most of you didn't. Thank you. And so also today is one of those lectures where we did a lot on the molecular orbitals and stuff for these pericyclic reactions, but actually what we really care about is how to use this kind of chemistry for making new molecules. Okay, so message to take home from this, the last couple of videos, is cyclic additions. You can use them to make 4-member rings too. It's much more difficult because remember the 4-member rings are the ones that, because of thermodynamics and kinetics, normally are the most disfavored. In this case, when you use nicely the certain substituents, especially the pericyclic reactions, you can actually make some very good 4-member rings, especially beta-lactams. We focus a lot on the video on beta-lactams because beta-lactams are substituted beta-lactams are ubiquitous in drug delivery, drug chemistry, drug design, and stuff like that. So beta-lactams are very active. So having some tools that you can use in the lab to use particular specific substituents, and you can make efficiently 4-member rings is very important. Then we'll see. You saw already some, we see some more. You saw already some of the use of the dipolar cyclic additions, even last year, although we didn't focus too much on the why is it forming and why is important, but actually sometimes they can make very nice compounds. Then I like to connect everything to chemistry that you can do in the lab. So, for instance, we saw that the 2+2 cyclic additions normally almost 90% of the times, let's say, they work only when they are photochemically induced. We saw that on the video. Quickly recap why does it work like that? Because you have 2 alkenes. Remember the first part of the cyclic additions when we actually use photochemistry to promote one electron from one orbital to the other. So we use this trick in this case. So one of them, the one which has the most compatible LUMO, actually one of the electrons get promoted in the 5-star orbital, which on one that is photochemically excited eventually becomes your new isocopy molecular orbital. The same way, exactly the same way as we have seen on the just cyclic addition, electronic cyclic additions on the first lecture, okay? So that part wasn't useless. In this case, you actually use it a lot for new chemistry. The most important thing is that if you have now one of the alkenes on the ground state and the other one photoexcited, you suddenly have 3 electrons which can do bonding and 1 electron only which is anti-bonding. This is why these compounds can form, but only when they are photochemically induced. Remember that we always said chemistry is a matter of energy. Formation of new bonds is a matter of energy. It's a matter of geometry sometimes, but especially it's a matter of energy. So when we want to use, instead of cycle additions, and we know that the photochemical cycle addition 2 + 2 work very well to form membranes. If you remember from the videos, what can be used instead of photochemically induced, instead of a photochemically induced molecule? So if it's not the photochemistry, the radiation of particular wavelength of UV light, which promotes one electron and makes the bonds happening, what can you do instead? You can eat, yes, but we said on the video, I discussed on the video the fact that sometimes heating only for this 2 + 2 is not enough. So you want to increase, heating is a good option anyway, because you want to increase the level of energy. Another way to increase the level of energy is to place substituents and to create reagents which are far more reactive than others. So for instance, on the beta, the formation of the beta lactams, which is incredibly important. Again, there are no many ways to form these 4 member rings. What can you use? Think about from the retrosynthesis point of view. If you want to do a retrosynthesis on this one, you can cut either here or there. So on the one side, you will have one alkene. On the other side, you have a species which is far more reactive. You remember what is this one called? Ketene. Excellent. So the ketene can be formed. We'll see how to form the ketene. Sometimes we form it in situ because it's far too reactive to be stored efficiently. Some of them can be stored, but most of them can be just formed in the Roboton flask and immediately used to form your beta lactams, for instance. This is a reaction that works particularly well on the microwave, for instance, because the heating on the microwave is very, very efficient compared to the heating on the bench. But let's focus on the reagent now. The ketene is another one, is one. The other one, if you want to cut the thing in the horizontal way. So whenever you do retrosynthesis, try to identify the 2 molecules which can be part of 2 potential reagents. So if you want to cut, let's say, vertically, you have ketene and an imine. If you want to cut horizontally, the same beta lactam, you have oxygen, carbon, nitrogen. So in this case, you have an isocyanate and a normal alkene. Also, the isocyanate is very reactive. Okay, so in both cases, the fact that the good thing of these beta lactams, because there are no many ways to form them, is that in both cases work. So you can imagine a variety of ketenes, a variety of isocyanates, and you can create a variety of beta lactams. How do you form mechanisms? How do you form the ketene? I give you the 2 reagents. What happens here? How can you form the ketene? Remember, typical trick, look at the starting materials, reagents, look at the product you have to form. What is going on? Why this compound actually forms a ketene? So what do we have here? What is right element? Guys, what is trielement? Why do you use trielement normally? It's base. Don't be shy. Normally, the easiest thing, the first one that should pop in your head is the correct answer. It's not a base. So what does the base do? Look at this compound. It takes a alpha proton. So if you take a alpha proton from here, what happens next? Look at the formation of the ketone. So you have your base. It is proton. It leaves a negative charge. What does a negative charge do? Look at the ketene. Again, it's carbon-carbon, especially why can you form the carbon? A new carbon-carbon bond. You have a good leaving group. So it's a very simple reaction. It's all chemistry you learned in the first year. So you have a base, you take an alpha proton. Remember, these alpha protons are more acidic than others, than normal. Then you have also a good leaving group, which is one of the crucial things on this kind of reaction. Okay. So basically, you have this one as a sort of intermediate. Your chloride. This one goes back here and it kicks out the chloride, and you form the ketene. Okay. Once you form the ketene, you can use with whatever quite activated also carbon-nitrogen bonds, and you can have selectively. Remember, one of the good things about these pericyclic reactions is that they are very selective. So if you have a very large part of the molecule on this side, but you can create this final acyl chloride with alpha protons, and you have an imine on the other side. Whatever is the other part of the molecule, this part clicks and it forms, let's say, a sort of A plus B kind of reaction. This is very important when you connect all this stuff to your retrosynthesis. Same as the DL solder that we saw in the past lecture. Whenever you have two terminal parts, which have, for instance, on the DL solder, which have two double bonds conjugated, a diene, and another part of whatever molecule, which has a good dienophile, in that point, only that point, selectively, it clicks and it forms the, let's say, a six-member ring. In this case, you can create beta lactams, which can be quite substituted in very good yields, as you can see. Stereochemistry quite well preserved. So there is a good way, like all the pericyclic reactions, there is always a good way to keep the stereochemistry. If instead you have isocyanate, the reaction works exactly the same way. This time is a movement of 2 + 2 electrons. And it works just heating up only because ketene and isocyanate are quite reactive. Okay. Otherwise, if you had other kind of double bonds, it won't work. Then, of course, remember that you can do a lot of other nice chemistry all around, and you can add your full beta lactams at the end. Always consider that we are doing this kind of cyclic reactions so that we can create new molecules. There is always some extra chemistry we can put on. Okay, exercise time. Read very well this question. I remember you always read very well the questions. The first reaction is the formation of the four-member ring. That we saw is very useful, but then there is an extra thing. This could be an exam question, because we don't only care about how to form the four-member ring. We care about how to use it in the lab. Let's say that you need to do an extra step. So in this case, for instance, you want to prove that the stereochemistry of this cycle addition is the one on your middle product, let's say. So that in order to prove, you reduce down part of this molecule, and only if the stereochemistry of this product is the one shown, only in this case, you can prove it. Only via the reduction, you can prove it that actually the stereochemistry is the one shown. So think about what happens first. And then we'll think about the reduction. Also, from the strategy point of view for the exam, if you have something on an exercise that you know perfectly, try to do that part first. You get good marks even if you miss part of the question. Okay, so focus. Maybe I shouldn't say that, but you should always focus on the part that we. you're more comfortable with. If you miss part, let's say you was a 7-mark question. If you miss the second part, which was 2 or 3 marks, you still get 4 marks if you can do at least very well the pericyclic mechanism. Okay. So what happens here? First part of the reaction is just deformation, the cycle addition, deformation of the formula. That shouldn't be a big deal. I will ask you to use the curly arrows to explain why this reaction works this way. Try to predict, remember it's a suprafacial attack. So if you think about the stereochemistry, you notice that these two are in phase. These two ester groups are in phase. It should be preserved in the final molecule. So the two ester groups, let's say, they stay in either both of them at the top or both of them at the bottom, depends on how you twist the molecule. What happens next? You have your stereochemistry. Now, we want to prove this is the right stereochemistry. What does the sodium borohydride do to this molecule? And this is something specific, which is going to be, this is worth to remember for any part, because you're going to use it for photosynthesis as well. Using selectively, let's say selective reagents, in this case, a reducing agent, to do selectively one thing only. If I give you sodium borohydride and you have ester groups and a ketone, what gets reduced? The ester of the ketone. Sodium borohydride is quite a strong reducing agent, but it could be quite selective. In this case, I can tell you the one gets reduced, the other one stays. Which one gets reduced? Ketone or the ester? The carbonyl of the ketone or the carbonyl of the ester? Which one? To answer that, we don't want you to remember. To answer that, you should think about which of these two carbons, of the two carbonyls, is more electrophilic. The carbonyl of the ketone or the carbonyl of the ester? Okay. The ester is more reactive or less reactive? More electrophilic or less electrophilic? Less. It's less electrophilic. From the very first moment we started using the carbonyl chemistry, we saw two different effects, the inductive effect and the mesomeric effect. The carbon of the carbonyl is always quite electrophilic because there is this separation of charges. If this one is a ketone, so it has aliphatic group, so not good living groups, here it has a certain electrophilicity, let's say. If it's on this one, remember that this oxygen has, this one is not working well. What is called the system that does that? The inductive effect is actually the effect of the two aliphatic groups. In this case, the two aliphatic groups are pushing electron density. That will be inductive. Or you can have an electron withdrawing group which is subtracting electron density instead. That will be the inductive. The one that shows that the electrons that hop between one and the other, and then eventually you have a system which makes something like that. This one is called mesomeric effect. by mesomeric effect, since there are two electrons, this is first year chemistry, okay? Since the two electrons of the oxygen can pop in this position, breaking the carbonyl, the moment that they break the carbonyl, they make the carbon-oxygen bond longer. The carbon-oxygen bond longer makes the carbon less electronegative and so less electrophilic. This is the reason why the ester, the carbon of the ester is less electrophilic than the carbon of the ketone. If you have sodium borhydride, sodium borhydride can easily reduce down onto hydroxyl groups, but it keeps intact the ester. It's very rare. There are examples in the literature where you can use sodium borhydride also to reduce down the ester group. But that depends. Remember, it's all a matter of how much energy is around. That always depends on the substituents which are around. Okay? So in this case, you can use sodium borhydride to reduce down simply the ketone. So once you reduce down the ketone and you keep the ester group, what happens is that if the ester groups are both up in this particular position, if you use a base and you take out the proton of the alcohol that you just formed because you reduce down the ketone, it can form this intramolecular ester group, okay, kicking out the methoxy group. So only if the two of them, the two ester groups are both up, only in this case, if you reduce down the alcohol which is underneath, can click to make the other cyclic ester. If you go to the NMR and you notice that you made this one, you know automatically that the stereochemistry that you started with was the correct one. Okay? So, cyclic esters, also known as lactose, proves the stereochemistry. Okay? What about this one? This one connects the exercises that we have done with the solder plus some other cycle additions and reductions or oxidation. Chemistry. What can we do here? If I tell you that this alcohol, the starting material, is completely stable until it's oxidized with chromium, for instance, but with whatever other oxidant. Chromium is this case. Sometimes remember that, okay, a little digression on this one. When you do retrosynthesis, for instance, I almost always ask you both the retrosynthesis and the forward synthesis. When you do the forward synthesis, you need to give me reagents and conditions. Sometimes saying just an oxidant is good, like in this case. Sometimes saying just I'm reducing with a reducing agent is good, like in most of the cases. In the case that we had before, instead, I would like you to tell me exactly, I would like to use sodium borhydride, because for instance, if you use lithium aluminum hydride, in this case, indeed, it reduces both the ketone to alcohol and the esters to alcohol as well. So sodium borhydride is a very specific reducing agent. In this case, I use chromium, you can use another oxidant. If you have this kind of question for the exam, and you tell me I need to oxidize, sometimes you just say, use this to say oxidized, that works for me. Unless it must be a specific oxidant. There are, for instance, specific oxidants which can turn alcohols into aldehydes without going to straight away to carboxylic acids. This is a very powerful reaction. There are 2 or 3 main examples that you can use. In that case, you need to tell me exactly what oxidant you're using, because if you tell me that you have a terminal alcohol and you say I oxidize it to aldehyde, I will ask you how, because if you use the chromate, it will go to carboxylic acid. as it is. If you use a particular chromate, for instance, I don't know if we will see with retrosynthesis, with the systematic retrosynthesis, but pyridinium chlorochromate, also known as PCC, a very good reagent that turns the spot to aldehyde without going further to carboxylic acid. In that, this is another case where you should tell me exactly what reagents you're using. Let's go back to this exercise. So what happens if you have the alcohol and you oxidize with chromium? You get your carbonyl. What happens if you have the carbonyl? What is the difference if you have the carbonyl unstable or if you have the alcohol stable? What is the difference between these two, considering what we studied so far? The carbonyl makes it. And what does it mean? It's correct. What the fact that it makes it more makes the carbon more hydrophilic. What does it do to this alkene? It makes it less stable, but especially from the pericyclic point of view, it makes the carbonyl is electro-withdrawing and it activates. This one becomes a dienophile. Well, before, as an alcohol, the alcohol itself has two lone pairs. It pushes electron density. It makes it less electrophilic. Carbonyl is pulling electron density, makes it more electrophilic, the whole thing. So this moment is activating this diene. If you have an activated dienophile, and a diene in this molecule, can you rotate the bonds so that you can create this cycle? This is something that you should see. Oh. Remember all the exercises that we have done with the free rotation of the bonds and putting all the double bonds to the diene. Remember, if you have a diene, conjugated diene in one molecule, and in the other molecule, or sometimes in the same molecule, you have a dienophile, you can do the solder. So you rotate the bonds, keeping the same geometry. Okay, this one doesn't have a particular geometry because it has two protons, but this one is trans, has to remain in trans. Then you rotate the bonds around, so that you put it next to your dienophile. Now, this one is a good dienophile. As an alcohol, is not. As a carbonyl here is a good dienophile. Then you can do your deal solder, and you can create your bicyclic compound. So if you have this question on the exam, you tell me the reason why when you oxidize it, it makes it less stable is because you can do the solder with this one, with the other one. Yes.
So now, you have to go the middle one.
Technically speaking, no, but it is correct. But if you do any intermediate, even when sometimes I say mechanism is not required at the exam. If you do the mechanism, you don't get it less marks. Sometimes doing the mechanism shows you, proves to yourself first that what you're doing is correct. So if you're doing it, it's fine, but you don't have to. But it has to be correct. If it's not correct and there is no mechanism, I cannot give you any marks. Just that. So the stereochemistry can be explained with the endo formation of diel solder. Remember that the diel solder does the endo is the one that should be in theory least favored from the thermodynamic point of view, but it's actually because of the hindrance is more stable. If you want to prove it, again, there is a nice molview.org, I think, but I got somewhere in my slides the website that you can use to create your models. If you minimize the energy, it shows you that these two protons are actually these ones. These two protons, which according to the diel solder, when you do that, go behind, go the back, it shows that the stereochemistry must be this one. So if you remember the superficial attack and the fact that these two protons have to go the same direction, and you do it correctly, it's great. If you don't remember, and if you can do the intermediate mechanism, it's better. You can prove that the correct stereochemistry with this Nice. And by the way, it's free. The software. Let's do this one now. Again, potential exam question. You have the same subject material. In two different conditions, you can have two different products. In this case, it will be explain the mechanism. If you do the mechanism with the curly arrows, please do it. If you can do it, please do it. Think about what happens. Remember, you have a starting material, and in both cases, on the either on the left or on the right, you have the product. You have a reagent on top of the arrow. It means something. If I put a reagent and I specify the reagent, there must be a reason. By the way, I didn't ask, but I think today I have a whole set of slides. I will carry on unless someone tells me I really need a break. I will do a break. But I think I prefer to carry on, especially the last part should be the last part of today with the segmental rearrangements should be faster because I don't want to linger too much on that. I prefer that you focus a lot on the pericyclic. You need to focus a lot on the deal solder. That's a strong tip and strong suggestion. Deal solder, and sometimes these kind of pericyclic additions. Especially focus on the mechanism of the formation and the stereochemistry. If you want to do the stereochemistry, either you can imagine the molecules of the starting materials and reagents in 3D, and that will be great because it means that you can visualize, or you can help yourself as usual. Sometimes I ask you specifically to use and to place partial charges. If I suggest put the partial charge at delta minus and delta plus, if you start from it's quite easy. You start with a big delta minus from the most electronegative atom, and then the next one has to be a delta plus, the next one to be a delta minus, and so far and so on. If you can do that, I am sure you can do most of that. So that's the chemistry. So what happens when I put this compound on the base? We saw that. This is a base. It's triethylamine because triethylamine is an organic base, it's a liquid, it's quite mild, can be used in this way. It's strong enough to be used in this way. But if you say you need to use a base, in this case, just a B minus, that will do for me. This is not one of the cases in which that specific reagent works and another doesn't. Triethylamine works. If you put sodium hydroxide, in principle, it works the same. I wouldn't use sodium hydroxide for this one, but you have alpha protons. The lone pair of the triethylamine takes one of the protons. What does it form? We saw that in the first few slides. The ketene, okay? What is the ketene useful for? If you see this reaction and you remember that you consider, no, you remember that you have this double bond on the other side, what are ketones good for? In the presence of another double bond, they can do cycle additions, okay? But you can do intramolecularly here or intermolecularly with this one. In the case of intramolecular, you obtain what product? This one. In the case of intermolecular, so two different reactions from two different reagents, you have the same ketene, but it reacts with this one instead. And it forms this product. Mechanism. Always remember this mechanism. I don't love the word remember, because if you know that these alpha protons are very acidic, if you use a base, you have a good leaving group on the other side, it should be automatic. You should click immediately with you that you can take out one proton, it remains a negative charge, that forms the double bond. How can it form the double bond? Only if you have a good leaving group on the other side. If you don't have a good leaving group on the other side, you won't form the ketene. Full stop. There is not something you need to remember. This is just basic chemistry from the first year. Okay, you form your ketene. Then, if you rotate the bond until you place it in a position that shows you the typical 2+2 cycle addition, then you can have the formation of this product on the left-hand side. If instead you're using the same, you're forming the same, exactly the same ketene, but you use that isocopy molecular orbital of another compound, then you use that double bond to form the four-member ring on this side. Okay? If I tell you, just guessing, which one is more favorable? Because in this case, you can have the formation of both products. Which one do you think happens more likely? There are ifs and buts, but if you just need to guess, what are which are faster, intramolecular or intermolecular? Intramolecular. So if you have to guess, then you need to prove it. Intra is within the same. So if you have the same diene and dienophile in the same molecule, and you can run a cyclization, the cyclization happens more likely intramolecularly, because the two ends, when the two ends are close enough to each other. How can you push towards the formation of the other one instead? In the lab. If something kinetically goes more towards this side, if you want to push for the formation of the other product instead, what would you do? Not in the lab. You know that there is competition with these two reactions. What can you do? Simple. Again? That could do, but if you drop it very slowly, if you give it enough time, especially with a mild base like triethylamine, you might have the formation of the fastest product, the kinetic. It might work, but actually, if you ask me, what would you do in the lab? I would say use a large excess of the other double bond. If you use it as a solvent, as soon as the ketene is formed, it is overwhelmed by the amount of the other double bond, and it reacts with that instead of reacting with itself. Okay, I will leave this one for home. Try to guess the stereochemistry. Try to prove, not to guess, to prove that the stereochemistry works exactly the way that I'm showing here. As usual, you can use the software or the molecules if you have them, or you can use the software to minimize the energy and to prove that actually all these protons which are out are all these protons. Okay, now let's go to the 1,3 dipolar cycle additions. They are rarer than the thermal 2+2, but again, they happen when you have one of the two reagents which is highly activated for that, okay? If you want to have a dipolar, it means that you have separation of charges in the same molecule. You have a minus and a plus in the same molecule, and they have to be one next to each other in order to form new 5-member rings in this case, or 6-member rings as well. We can produce a 3 atoms, is 3 atoms, but it's always 4 electrons, because in order to have a good cyclization, pericyclic reaction, you need to have at least 4 + 2 if you have a sort of deal solder, because the 2 + 2 only work photochemically, like we saw at the beginning, or when you have ketenes, isocyanates, something very activated. So this was a typical dipole. And this is the reaction that happens. So again, 1, 2 electrons from the pi bond, 2 electrons are coming from the negative charge on the oxygen. The negative charge on the oxygen is there because a nitrogen with 4-member rings is always positive. It must have a negative charge to counterbalance it. This is the compound you form. Again, a very efficient reaction. Nitron. Confused about what? You said you're confused. Yes. If it's chemistry, I might try to help you. If it's something else, it's recorded, so you can watch it again. But the first 5 minutes, what did we say in the first 5 minutes? We just talk about why the 2 + 2 happen photochemically. Sorry? The bracket.
The 2 + 2, why is it in a bracket?
The 2 + 2 is in a bracket because it's an intermediate. Whenever it's in a bracket, in a square bracket, it's an intermediate. It means you cannot isolate it. So when you have, especially in the beginning, no, it's totally fine. So when it's a bracket, you can put within brackets, you can put the little kind of sign outside the bracket. It means that it's an intermediate. It means that you are creating in situ. You are doing something in your bottom flask, which creates a species which is so active that cannot be isolated, but still it forms and it reacts with something else. When it forms and reacts with something else, sometimes we put it in a bracket to show that this is the intermediate that it forms, but you cannot take it out, isolate it, store it, and use it whenever you need. It forms in the reaction and is consumed in the reaction, okay? And the first part, we mainly talk about why do you have that kind of intermediate and why it forms 2 + 2 cycle additions only photochemically. In this case, again, this is on the video, so I don't want to stay too long on that, but the linear dipoles or trigonal dipoles always forms this kind of 1,3 dipolar cycle additions. If you want to remember something, because remember it helps, it's always the atoms are always 4 electrons. Only 4 + 2 electrons actually form a new cycle for this kind of reactions. It helps if you remember that the central atom on these compounds, the very activated species, the central atom is never a carbon. You need to have, for instance, here the nitrogen, which forms 4 bonds, so it stays positive, automatically places a negative charge in the oxygen next to it. If it was a carbon, it wouldn't happen. Then all the rest of this information can be helpful, but I think the first 2, maybe 3. This one is quite always have formal charges. It's quite obvious, I think, because if you don't have a formal charge, you wouldn't call it dipolar. Exercise. You have this nitron. You do your reaction to form the 5-member ring, the 1,3 dipolar cycle addition. And then remember, when there is 1 and then 2, it means that between 1 and 2 is the opposite of what we were talking about with the square bracket. If there is a 1 and a 2, it means that the product that comes from 1 can be isolated. And then you do the workup, like if you were in the lab, you do the workup, and then you do the second part, using, in this case, lithium aluminum hydride. Okay, when you have this sequence, when it's everything together, you think, I might put everything together. You have 1 and 2, it means these 2 reactions are separated one from another. So again, in this exercise, try to do first the mechanism, play a lot with the mechanism, with the movement of the arrows, so they form the cyclization. Then, like in the previous exercise, the second part is not optional, but I would like to focus a little more on the first part. The second part is extra chemistry that you will do alone, if you needed that compound instead of the second. If you can do that, if someone make the first part of the reaction, can someone tell me why do you need the lithium aluminum hydride in the second part? It is a very strong reducing agent. What it reduces down? If you do the first cyclization, you will notice. It's correct. So if you have lithium aluminum hydride, clearly you want to, actually it's quite a strong reagent. Remember, if you use lithium aluminum hydride in the previous exercise, it will reduce down both the ketone and the ester group, and that wouldn't do. For that reaction, you need specifically a reagent like or the same strength, not exactly only sodium borohydride, but something of the same strength as the sodium borohydride. Lithium aluminum hydride is far stronger, much stronger than the sodium borohydride. It reduces down almost anything it finds. So the first reaction, I hope someone tried it. Remember, guys, that when you see the exercise and you see the solutions, everything looks easy. When you have the white paper, and at exam you have the white paper, I'm afraid, this is the moment that we really want to rely on your mechanism and curly arrows, okay? Practice a lot with these exercises. So the first reaction is like the one that we saw. We just use the nitron to do 1,3 dipolar cycle addition. You form this nice compound. It's oxazole, because it has oxygen and nitrogen in the same heterocycle. We saw some of them in the second year when I did as heterocycle. What happens now if you use lithium aluminum hydride? The first reaction is clearly it reduces down the part which is more electrophilic. In this case, this bond between the carbon and the nitrogen. So this one is as electrophilic, it is no more electrophilic than a carbonate. Okay, this one is as even more electrophilic than a normal carbonate. What happens next? Guys, what happens next? Lithium aluminum hydride carries on, and clearly it breaks the oxygen-nitrogen bond, which is not super stable. And you form your desired compound. Let's remember the stereochemistry. Guys, now, quick summary, then we'll move to the final part of the pericyclic reaction. I'm sure you're going to be very happy, but please practice with those. So let's summarize a little bit. Cycle additions are characterized from being one-step or concerted reactions. So everything occurs in the same kind of intermediate state. It doesn't go step by step, slow back. Not going step by step. Sometimes it helps because it prevents potential side reactions. Normally, ideal solve that kind of reaction, either if it works or it doesn't. It doesn't have something intermediate because the step is concerted. Either it goes that way or it stays as the two starting materials. We thought different ones, thermally induced and photochemically induced. The thermally one should be a 4N plus 2, whereas the photochemical one should be 4N to work well. If you do molecular orbital and if you do exercises to prove with the molecular orbital as well. That this one is true, you will see why. Chemistry always wants the formation of the most stable compounds. So you need to consider that sometimes you put these two reagents, dienes and dienophils, for instance, in reaction, because eventually the product you form is more stable than the two starting materials. If that happens, the reaction becomes very efficient and it moves towards the formation of the product. In this case, for instance, if the equilibrium goes on the right-hand side, a thermal reaction happens because you form two new sigma bonds, which are stronger than pi bonds. Stronger means more stable. More stable means more favorable for the formation of product. In the photochemical cycle, addition is similar because it loses pi bonds, and it's also absorbing energy because you're using energy to photoinduce it. Always consider the stereochemistry. I really love to put exercises at the exams talking about tell me the stereochemistry or prove the stereochemistry of this particular pericyclic reaction. So please practice with those. This is the typical movement of Carl arrows that I would like to see. When I say, please do the mechanism. If there is a deal solder, please show me that you know how to move these three arrows in this case to put the bonds in the right place. This one could be final part of a very large molecule on this side, or a final part of a big molecule on the other side. When you have this kind of system and this that is an electron withdrawing group, this reaction works specifically in this way. So if you have a macromolecule A and macromolecule B, but the terminal part is a diene on one side, dienophile on the other side, the two reactions form a very large molecule. So sometimes we will see in retrosynthesis, sometimes a very large molecule can just be chopped initially in two parts, and you treat them as they were completely different exercise, different molecules. Now, first of all, any questions on those? I don't want to press even more the fact that I really like to put exercise on this side. Anything which is not clear and you want to discuss now? What I really like you to learn is clearly how to use this kind of stuff potentially in the lab. So be careful when you have the possibility of formation of a 6-member ring. If you can do it by a pericyclic reaction, please do a pericyclic reaction because it's very selective. Please consider the fact that you need to have certain kind of geometries and certain kind of substituents if you want the reaction to be efficient. The fact that you don't have them doesn't mean it's not going to happen. But you might want to specify at the exam, but this one is not activated, so I need to use higher energy. So for instance, I put up the temperature, or I use very concentrated conditions so that the impasse of the different molecules is more likely. Okay. Let's move towards the very last part. I don't want to stay too long on that because I use them, but not as much as the Elsorder-like reaction or the other kind of cycle additions. Claisen and Cobre arrangements are really useful, but sometimes they are a little too, I consider them a little too difficult to spot, considering that you have to study a huge amount of stuff. So I try to be, I'm not saying that I'm never going to use them, but I say that it's more rare. But if you watch the video, I left a question. So for instance, on this one, you have your Claisen rearrangement. But instead of starting from the acetaldehyde, which is this one, you start from an equivalent of the acetaldehyde, because the acetaldehyde is not super toxic, but it's not super nice. It reacts with itself. It tends to react with itself. Why? Because it has alpha protons. It's very easy to analyze. It has alpha protons, so it has an enol. The enol form on one can attack the non-enol form of the other, and it keeps cyclizing. You saw that in a huge part with June last year. I always use the same kind of concept, so please remember it's true. It's not just on paper. So sometimes you prefer to use in the lab an equivalent of the acetaldehyde. In this case, this one with 2-methoxy. Can be used in different forms. If you have a methyl and this 2-methoxy, it works instead of the aldehyde, it works with a ketone. So with a methyl on this side instead of the aldehyde. You can carry on with the orthoester, it works with amino groups. Now, for a moment, forget about the arrangement, the reason we're going to use the pericyclic reaction. Let's focus for the moment on the use of this equivalent of the aldehyde. Looking at the different reactions, you use it here, this one, and this one, and this one, this one, this one, and this one. What is the common thing? Why this one is quite useful? What is the mechanism that actually makes it an equivalent of the acetaldehyde? You are in acid conditions, remember? What happens to this one? Why it's so easy to use? What happens if you put this one in the presence of an acid? You use, okay. This one is an acetal. What we studied them for the first time. We met them for the first time in the first year. What is an acetal usually? How do you use an acetal? What do you want to make an acetal? Sometimes. If you want, if you help, consider that this one eventually is the equivalent of this one. What do you do with the acetal normally? Not in this case. In this case, you use it to stabilize the acetaldehyde. But why do you stabilize it? What happens to the acetal? What is the acetal compared to the carbonyl? Not talking about the reactivity and basicity. So actually it makes, and that might help, it makes the carbon of the carbonyl, of the former carbonyl, less electrophilic. When do you want to make, when do you have a carbonyl, for instance, and you want to make it less electrophilic? Because you don't want to react with a nucleophile on the other side. So sometimes in order to make a new, less electrophilic, you make a new molecule. What is that? Protecting groups. So the acetal is the protecting group is one of the most common protecting group of the carbonyl. And for a very good reason, because it makes the carbon of the carbonyl, the former carbonyl, less electrophilic. So if you have something which would attack the carbon, let's say a Grignard reagent, is a strong nucleophile, it will attack immediately a carbon of the carbonyl of an aldehyde. If you turn it into the acetal, it won't do it because the carbon is not electrophilic anymore. In this case, we're using for a different way. What do you remember, if you remember anything else on the acetal? Placing them and removing them. You can do both of them in acidic conditions. You can place them in, and you can turn a carbonyl into an acetal in strong, concentrated, let's say, acidic conditions. You remove it in water condition, acidic water conditions. Why is that? Because it's called hydrolysis. So to have a good hydrolysis, you need to have water. So mild acidic conditions, especially if it's a water acid, they say HCl, which in solution always can, at maximum at a 35% concentration, all the rest is water. So you use something which contains water and an acid, and you can turn back the acetal into the carbonyl. What happens to this compound as soon as you put it in acid? Chemistry speaking, simple as that. Where does the proton go?
The oxygen.
In the oxygen, okay? Let's see here. Why do you want to do that? Because this one now, remember the same way how in the past we used, I don't know, protonated version of something, let's say an alcohol, you protonate it because the hydroxyl group is a horrible living group. But if you protonate it, it becomes water. Water is an excellent living group. In this case, you create protonated methanol. Methanol is an excellent living group. So what does it do? It leaves methanol stays happily in solution. And you have this species. This is general organic chemistry, guys. And I'm trying to do it because I want always to mix the slightly more, I want to show you that the slightly more complicated organic chemistry actually comes from the very basic organic chemistry that we studied from the first year. So you have this one now, again, since the methanol goes out as a neutral, it must leave the positive charge behind. Where does it go? In the other oxygen. In this case, remember that when you have something like that, the positive charge is never really on the oxygen, which is strongly electronegative. So it pulls electrons, making this carbonyl far more electrophilic. Now this carbonyl can be attacked by the alcohol on the previous slide. If you put, it's like when you say, on the first year we said, if you want to activate a carbonyl because it doesn't want to be attacked, yes, it's a good electrophile, but in this case, for instance, in the presence of an alcohol, doesn't want to be attacked by the oxygen of the alcohol, which is not a great nucleophile. Either you make something more nucleophilic, let's say sometimes taking out the proton of the alcohol and making the alkoxide, or you can do the other way around. You activate the carbonyl and you make the carbonyl more electrophilic so that even a weak nucleophile will attack it. This is one of the cases. So in this case, you form your first part of the cycle. The proton can get removed even just by simple water. And take the proton here, creating more H3O plus, which stays in solution. It's already in solution, so it's happy to stay there. Then, again, you have another living group. You still have acid. You can protonate this one, create more protonated methanol, comes out, gets neutralized. Now, this one is the new compound that you can use to make your first Claisen rearrangement. So how does the Claisen rearrangement work? Always a movement of the arrows. And then eventually, it moves things around. It's much easier if you see it with an exercise. So if I show you this one, I tell you that it works in a Claisen rearrangement. It does a Claisen rearrangement. Can you show me where the two R groups will be in the final molecule? Can you show me the final molecule? Think about it. You always want to put it in a way that reminds you of something like that. Okay? At some point, at some level. So one of them could be this double bond. You want you rotate, you have that. What does it do now? 'Cause if you can rotate the bonds so that it shows something like that, which is more familiar to you from the pericyclic reaction point of view, you now can do your rearrangement. You know that if you have that oxygen over there and two almost potentially conjugated double bonds, because they're not, they're part of the same molecule, they're not conjugated, there is no bond in here, but you can make a good bond if you make a pericyclic reaction, in this case, a rearrangement. Rearrangement means simply always, remember, chemistry always wants to go to the ground state as much as possible. If a rearrangement happens, it means that the product that you form from the rearrangement is more stable. That's it. It doesn't happen because we are funny, we want to make life more complicated. It happens because it happens. Because nature decided that that one, if you study it very well, you actually notice that actually has a lower level of energy of the starting material. So if you move the arrows, you can form your new bond between the two double bonds. You form your intermediate. In this case, for instance, you can say that you can put this one in brackets, okay? Because this one, you will never isolate this one. Why do you never isolate this one? Why would you never be able to isolate this one? Again, simple organic chemistry. Why? Too unstable? Yes. What would be the alternative? This one is too unstable. So what would be the stable? What would the stable version be? Simple as restoring the aromaticity. Same thing as when you have a potential carbonyl. If it can go back and restore the carbonyl, it will do. Always think about it. It will always try to go to the minimum state of energy. The carbonyl chemistry, the carbonyl is so useful because it's very versatile, but it's more stable as a carbonyl than, let's say, as an enol. If it can go back as a carbonyl, it goes back as a carbonyl. What the aromatic groups, even more. If you have even a chance to form an aromatic group, it will do it. Cancel everything so that you can see better. Okay, so first of all, move the double bonds in a position that it will look familiar. If you see different double bonds, try to put them in a conformation that reminds you of a potential Diels-Alder-like, pericyclic-like reaction. Then you move things around because now you know that in the system, everything can be rearranged. It means that this whole group shifts to the aromatic part, breaking the aromaticity. It breaks the aromaticity, but it doesn't want to be, the aromaticity doesn't like to be broken. It prefers to go back to aromatic. If it can go back there to aromatic, you have two options. The whole group moves back forming the starting material, or it for something which is more stable. In this case, this one is more stable, but comes this product instead. So once you have this conformation, it doesn't easily go back to the original starting material, because the original starting material with the carbon-oxygen-carbon bond is more unstable. So there is always a reason. Can you do this one now? Considering the same shift and rearrangement. This one will be a sequence, a cascade of hydrogen shift. This is something which that should be the drill, so let's wait usually 10 seconds, not 10 minutes. If it stops, otherwise we'll leave it. Okay. So that uses something that sometimes organic chemistry really likes, isotope labeling. So you can follow this reaction. The fact that you form different isomers, sometimes using this, producing this hydrogen shift, can be followed by deuterium. You can follow by deuterium, because if you do an NMR of each single isomer, each NMR will have different multiplicity, chemical shift, something like that, because you can see the protons on the NMR, you cannot see the deuterium. So depending on the position of the deuterium, you can have either one isomer or the other. So this is a series of 1,5 sigma tropical wave, which normally is considered as a side reaction, because you don't expect that it happens, then it happens, you find what should be in your mind a simple spot on the TLC, and you find 3, 4, depends. Then, of course, people will do TLC in a bad way and people in a good way, but the people who do the TLC in a bad way are not following. No way. Never mind. You can move the deuterium. Remember that it's a hydrogen shift, but the deuterium is basically hydrogen with an extra neutron. But the chemistry is the same. So if a hydrogen can shift, the deuterium can shift too. So you can put with a series of 3 arrows movement, you can put this one in this position. Now it can either go back to the original or it can move down. Imagine you have different subsequence around here. Even if you have one subsequence, even 1 meter here, will make losing completely the symmetry. Your NMR will look like a mess. Your TLC will look like a mess, even if you do it well. Okay, so phase and condensation sometimes is very useful from the chemistry point of view, because if you can form this one with a reaction, let's say that this one comes from the photosynthesis point of view, this one comes from a phenol. And then you have the equivalent alcohol on the other side. Reaction is easy. It's a condensation. It forms an ether, but this ether is not stable. You heat it up a little bit, and it rearranges to form this one. So ideally, you should see, it's not an easy one, but you should see from the retrosynthesis point of view that if you need to have this kind of reaction, you might start from phenol and this alcohol, because then it will undergo also Claisen rearrangement. Remember that we don't want to see only this kind of reactions from the mechanism point of view. We want to make it useful for the lab. If you were in the lab, you need to make this compound. It's not really intuitive, but actually, if you know the chemistry of the Claisen rearrangement, you can imagine that you can start from very easy and cheap starting materials. Don't know what happened to my Zoom, but I hope I'm still recording. Okay, now, one of the last ones, because today I think we're going to die of pericyclic reactions, and I don't want to. Try to do this reaction and think about why, if you can imagine making this ether, like in the previous example, instead of moving next to the carbon like you would expect with a typical Claisen rearrangement, it goes there. Try to think about why it would happen. If you do hold the mechanism, and if you move the arrows in the proper way, you will see immediately. Remember that the key is that if you have something aromatic and it wants to be aromatic, it will try to find a way to become aromatic again. Nature says that. So try to do the very first Claisen rearrangement with the movement of the 3 arrows, and then show me what is the intermediate step. if you want, it may help, think about the same reaction without these two methyl groups. If you don't have these methyl groups here, what would the rearrangement be? Then you add the methyl groups and see what is the difference. That should help a lot. Did anyone try, succeed? No, I will do like that. If you have first one, this one I will do uniforms. Then you want to restore the aromaticity. So this photo. And it's driving crazy, sorry. So that will be do it without the methyl groups. Let's see more clearly. Okay. You want to restore the aromaticity, so immediately you lose this proton in from this one. But if you have in the ortho position a methyl group, either side, in this case both sides, because if you have on one side only, the rearrangement will occur in the other position. If you have it in both sides, now suddenly, instead of having a proton here, you have a CH3 that won't move. So the only alternative is go back to starting material. If you have this kind of situation, restoring the aromaticity is impossible unless it goes back to the original starting material. In this case, you don't see anything in your reaction. But if you leave it long enough, when it goes to this part, which you can again put in brackets because you cannot isolate this one. If he wants to go back to starting material, it goes back to starting material. But if he wants to create a new stable, even more stable aromatic compound, you can imagine it does that. Okay, there is always free rotation around that. Now, the double bond is this one, and on the other side of the molecule, this one. The first one is a Claisen rearrangement. This one will be a COP rearrangement. You do this movement of 3 arrows, and instead of going back to starting material, it will create this COP rearrangement. Remember that the difference between the COP and the Claisen is that on the COP is only carbons. On the Claisen, it must be the ether bond, or carbon, oxygen, carbon. So basically, it carries out this rearrangement from something which is even more stable than the starting material. Okay? So this one forms this one. It cannot go back to aromatic on this side unless it moves back to oxygen. So to restore aromaticity here, you can imagine only this carbonyl breaks of double bond here, and this one has to migrate to restore the subtle material. But again, there is free rotation. So if you put these two double bonds in a position that suggests it's still, that's still two double bonds, I can do a copper arrangement that migrates. You form this non-aromatic product, which you can always say, again, in bracket, because you cannot isolate this one. And a simple addition of water. Just need water. Water is good enough. If one of the compounds becomes aromatic, water is nucleophilic enough. Normally, water is a horrible nucleophile, but water in this case will be nucleophilic enough because this proton really doesn't like to stay there. Because if it moves, it aromatizes the ring. Okay. I have few more exercises, a couple of them plus a few more molecular orbital, but actually, I think you're quite tired today. You're less reactive than usual. Even less reactive, guys. This one easy. This one comes from the first. I just would like you to think about and to prove it. It comes from the first table that we used on last week. So think about all these movements. So to form new product, if it's aced thermal cyclization with a conjugated tetrahene, thermal, it means not photochemically activated. Trying, remember, try to make your psi of all the different molecules, and then you decide. Thermal, trying 4 even number, you expect an anti-partial rotatory movement. Try to do all the others and prove that actually works this way. If you want, use a tetraene, do a thermal cyclization, use mole view to prove the stereochemistry, and try to practice and convince yourself that it's actually working. Okay, all the rest is just extra exercise on molecular orbitals, but I don't want to. They're not completely. I mean, you can do without. Let's put it this way.